Hello everyone. In the previous class we have started with the module number 3 and we have discussed about predefined primitives, that is AND OR gates and buff and if gates. In today's class we will see an example using gate level modeling. So first, array of instances. Instead of writing the multiple line code, if the instances differ only by the index number of the vector which they are connected, then it can be written using array of instances. So there are a number of situations comes while coding the program or writing the program using gate level modeling, in which the repetitive instances are required. So whenever the repetitive instances are required, they are going to be simply written using array of instances. So these instances are going to be different from each other only by the index of the vector to which they are connected. So to simplify the specification of such instances, Verilog HDL provides an array of primitive instances to be defined. So it's very easy to make use of array of instances whenever the repetitive instances are required in your program. For example, so this is an example simple array of primitive instances. So observe here, wire is a vector 7 down to 0. That means there are 8 wires out comma in 1 comma in 2. Now observe here the basic gate instantiation. So for example, here the NAND gate is used, NAND, then the instance name N gate. So it is optional 7 down to 0 instantiation out comma in1 comma in2. So this is nothing but a array of instance. So this is its equivalent instantiation. If you want to write in detail, so the below one is shown. This is equivalent to the following 8 instantiations. That is, instead of declaring that wire as 7 down to 0, you can separately write NAND instance name NAND gate 0, N gate 0, out of 0 comma in1 of 0, I comma in2 of 0, semicolon. Similarly, for the next gate, NAND N gate 1 out of 1 comma in of 1 comma in2 of 1. Like this you can write for the instance names N gate 0 to N gate 7. So there are 8 different NAND gates. So instead of writing this whole 8 instances, observe the instances here. So it is changing only in the index number from 0 to 7 everywhere. For the instance name N gate, it is changing different only from index number, that is 0, 1, 2, 3 up to 7. Output out also, it is changing from 0 to 7. in1 and in2 also, they are changing from 0 to 7. They different only in the indexes. That's why instead of writing the whole 8 line code, you can just use the above code, that is NAND N gate 7 down to 0. So 7 down to 0 means it is going to instantiate from 0 to 7. The 8 line code will be just, it is equivalent to the below 8 lines. So NAND N gate 7 down to 0. Just you need to use a instance array of instance out comma in1 comma in2. So this is just an equivalent to all these 8 lines. So this line, so this is very easy to use. So this is an example of a simple array of primitive instances. So whenever such kind of any repetitive instances appear in your program, so instead of writing the whole program, just you can use the array of instances. Now example we are going to discuss today is gate level multiplexer. So this is a program we are going to design for a 4:1 multiplexer using gate level modeling. So we have already seen what is the components of module and how to instantiate using gate level modeling. So we are going to see the example using gate level modeling, that is 4:1 multiplexer. So as we know that 4:1 multiplexer consists of 4 inputs, 2 select lines and 1 output. Multiplexer is a data selector. That means output is nothing but it selects a particular input itself based on a select lines. Input is routed to output, but which there are number of inputs, but which input is routed to output, that will be decided by the select lines. So that is the working of multiplexer. So multiplexer serve a useful purpose in a logic design. So multiplexer is a combinational circuit that you might have studied it in digital electronics subject. So you must know the combinational circuit, that is multiplexer, its schematic diagram, its truth table for 4:1 multiplexer, then the logic equation or Boolean expression, and a circuit diagram or logic diagram. So they can connect 2 or more source to a single destination. So this single destination means output is only 1. So 4:1 multiplexer having 4 inputs, so they are going to connect to a single destination. They can also be used to implement Boolean functions. So we will assume for this example that signal S1 and S0 do not get the value X or Z. So see here, as we know that the values are 0, 1, unknown value X and high impedance value Z, but out of this here we assume that signals S1 and S0 will have only two values, 0 and 1, for sake of simplicity. So this is a schematic diagram, first one, of a 4:1 multiplexer. So as you can see, 4:1 multiplexer consists of 4 inputs, I0, I1, I2 and I3, and 2 select line inputs, S1 and S0, and 1 output out. So whenever the select line S1 and S0 are programmed, that is whenever it is S1 is 0, S0 is 0, output is I0. I0 is routed to out. Similarly, when S1 is 0, S0 is 1, I1 is routed to out. For 1 0 input, I2 is routed to output, and finally when S1 and S0 both are 1 1, I3 is routed to output. So based on this, the Boolean expression for this 4:1 multiplexer will be out equal to S1 bar S0 bar into I0 plus S1 bar S0 into I1 plus S1 S0 bar into I2 plus S1 S0 I3. So this is the Boolean expression for the 4:1 multiplexer. So using the truth table, you can write this expression. And this is a logic diagram for 4:1 multiplexer. It's a gate level diagram. So observe here, I0, I1, I2, I3, S1, S0 and out. These are the original input and output list as per the schematic diagram. Then we have few more names within the circuit diagram: Y0, Y1, Y2, Y3 and S1N and S0N. Observe here, so when in a gate level modeling, other than the schematic variables, if you have any wires in between two gates which are not named, which do not have any name, you can name them arbitrarily. Those are again identifiers: Y0, Y1, Y2, Y3, S1N, S0N. S1N nothing but S1 bar, S0N is nothing but S0 bar. So you can name as per your requirement for the program. As you can observe from the Y0, that is that AND gate output to the OR gate input, we do not have any name, so designer has given the name as Y0. Similarly, all the other AND gate outputs connected to OR gate inputs which earlier do not have names, so that has to be given by the designer. So Y0, Y1, Y2, Y3 are the names given by the designer. Similarly, inverters or NOT gates, NOT gate outputs are connected to AND gates. So those also do not have had names earlier. So you can give the names as per your requirement. So here the names given is S1N and S0N. It is not mandatory that you have to give the same names. You can use any other names other than the I0, I1, I2, I3, S1, S0 out. Do not use the same names. So these are the identifiers. So first draw the logic diagram for the 4:1 multiplexer. So after drawing the logic diagram, list all the inputs, select lines and output. Then identify the in between wires and give the wire names. As in here, Y0, Y1, Y2, Y3, S1N, S0N. So after doing this, so in a gate level modeling, the circuit diagram itself is the requirement. If you draw the circuit diagram, you can easily write the coding of the any combinational circuit or sequential circuit. So here we are discussing about 4:1 multiplexer. If you are able to draw this circuit diagram and if you are able to write all the inputs, output and wires, it will be very easy to code. So see here, the same thing is described here. The logic diagram has 1-to-1 corresponding with the Verilog description. Two intermediate nets S0N and S1N are created. They are complements of input signal S1 and S0. So S1 and S0 are the select signals. Its complement values are S0 bar and S1 bar. Internal nets or nets can also be called as wires. So those wires Y0, Y1, Y2 and Y3 are also required in the gate level programming. Note that instance names are not specified for primitive gates. That is, within a NAND gate, within a AND gate, OR gate or NOT gate, we have not given any names like N1, N2, N3, N4, NOT 1, NOT 2 or R1. Like this, you can also give the names if you want to use the instance names. So that is not considered here in this example because instance names are optional. Either you can use them or you can skip them for a predefined primitives. So instance names are optional for Verilog primitives, but they are mandatory for instances of user defined models. If you have a user defined models, in the next example, in the next class we are going to discuss. In that example, as it is a user defined module, we have to use the Verilog primitives, that is instance names. But for the predefined primitives, we do not require, or it is optional to use the instance names. Now this is the program for the 4:1 multiplexer. So see the program: module followed by module name. Module name can be given by the user. So as it is a 4:1 multiplexer, give the appropriate name. Here the name given is mux 4 to 1. So like this you can give the name. So module name are compulsory part. Then as this 4:1 multiplexer is having some ports, list all the ports. So that is out, refer the schematic diagram for the port list: out, comma I0, comma I1, comma I2, comma I3, comma S1, comma S0. Then termination signal. So see here, only the original ports are specified here, not all the intermediate wires. Remember here. So port declaration. After this, we have to declare the ports, which is output, which is input, or else you can also use make use of a ANSI style, in which the list declare and declaration both can be done here itself. So you can use any of the method. So this is the easiest method. Here out is the output. So output out inputs I0, I1, I2, I3. Then there are two more inputs, select signals, that is S1 and S0. So this is the declaration of ports. Now you can declare the internal wires. So as we have drawn the gate level circuit diagram for the 4:1 multiplexer, and we have declared intermediate wires Y0, Y1, Y2, Y3 and S1N and S0N. They are nothing but the wires or nets. So you can make use of a wire. So it is a keyword wire S1N, comma S0N, and there are four more wires: wire Y0, comma Y1, comma Y2, comma Y3. So up till this much the declaration part is over. Now we are going to design the program, that is logic of the program, using gate level modeling. That's why we have to instantiate the gates. So to write the instantiation of the gates, you have to refer the each and every gate in the circuit diagram. So first we are going to instantiate the NOT gate. So NOT gate, as we are not using the instance names, so instance names are skipped here. So NOT gate, it is a predefined primitive, that's why NOT followed by first output, then input. So output of the one of the NOT gate is S1N followed by input S1, termination sign. Similarly, another NOT gate is there. For that, S0N is the output, comma S0 is the input. So NOT in bracket S0N, comma S0, semicolon. So NOT gate are already done, the gate instantiation. Now we have to do the instantiation of the AND gates. Observe all there are 4 AND gates in our gate level circuit diagram. Each and every gate has to be instantiated. So observe the diagram again. You can draw that circuit diagram in a paper and you can see this program while seeing the program. So AND gate, it is a predefined primitive, that's why AND followed by its output is Y0. Observe the figure, then write the instance names. Output of AND gate is first AND gate Y0, then its input is I0, S1N, S0N, semicolon. This is one instance of AND gate. Like that, there are 4 AND gates in your circuit diagram. So write the instance names of all the 4 gates. So that is nothing but a 3 input, that is nothing but a instantiation. So similarly, second AND gate, and y1 is the output, I1 comma s1n comma s0. Next, similarly all the other AND gates are instantiated. Now we have OR gate. We have 4 input OR gate. Observe the 4 input OR gate. Its output is out. Then there are 4 inputs for that, y0, y1, y2, y3. Those are the wires. So instantiation part, OR followed by first output out, then its inputs are the wires y0, y1, y2, y3, semicolon. So this is the end of the module. So like this you can code the 4:1 multiplexer. So this is the internal part. To execute this program, you need to write the stimulus block or test bench. Writing the test bench is as important as writing this program, because to execute the program, to observe the output on the computer screen, you need to give some input values, then only your program is going to produce the output. So for that purpose you have to write a stimulus or test bench for the given program. So stimulus for the multiplexer. So here it is a top module. Stimulus is going to be a top module. So here define a stimulus module which do not have any ports. So this top module is nothing, do not have any ports, because it is nothing to communicate with the external environment. So it is going to communicate only with the internal parts. That's why it do not have any ports. That's why module stimulus, there is no list of ports here because ports are absent. Then define the variables to be connected. So from here, from this stimulus module, you need to connect to the module 4:1 multiplexer, mux 4:1. So that's why you need to declare variables to be connected to the inputs. So inputs are taken as reg and outputs are taken as wires. Go to the refer the port connection rules, so you'll understand. Reg I0 in 0, in 1, in 2 and in 3. So these are the 4 variables. Then we have 2 more register variables, s1 comma s0. Then we have to declare the output as wire here in the stimulus block. So wire output, you can either use the same name or you can change. Now instantiate the multiplexer. So mux 4:1, instance name is used my mux, list of variables, output comma in0, in1, in2, in3, s1, s0, semicolon. Now, so this part, initial and begin, we are going to discuss this one in the behavioral modeling. So to start any block in a behavioral modeling, we have to use initial, then begin is nothing but grouping it is. Then you have to provide some values for the input signals, any values in binary, either it can be 0 or 1. So any combination of values, so that is provided here. Set of input lines in0, in1, in2 and in3. So provide some values. In0 is equal to 1, in1 equal to 0, in2 equal to 1, in3 equal to 0. It is not mandatory that you have to give the same input values. You can give any binary values. Now you can display them. If you want, you can display them. So for that, use a delay signal, delay value. So #1 is a delay value, and we have discussed system tasks. So using the system task, that is $display, we can use to display the values of input signals. So all the input signals are in binary. That's why display function is nothing but it is a printf statement in C programming. Same way here also, in a double quotation mark, in0 equal to %b, in1 equal to percentage b, declare all the input signals in binary, then list them in0, in1, in2 and in3 separated by commas. Now you have to select the signals. We have 4 combinations of select signals for S1 and S0, 0, 0, 0, 1, 1, 0 and 1, 1. So display all of them. First combination, S1 equal to 0, S0 equal to 0. Using the same display function, use that S1 and S0 in binaries and output value. When S1 is 0 and S0 is 0, what is the output signal? So output is also in binary because we are using a multiplexer. Multiplexer provides values in 0 and 1. That's why output is also in binary. Percentage slash n is used to go to the next line. So S1 comma S0 comma output. Like this, write all the combinations of S1 and S0 for 0, 0, 0, 1, 1, 0 and 1, 1 and end module. So this is how we can write the module stimulus or test bench. There is one more method of writing the test bench, so that will be discussed in the later class. So just now we can observe the output, how the output is going to appear on your screen. So the output of the simulation is shown below. Each combination of the select signal is tested here. That is, each combination means for the different values of select signals S0, S1 and S0, that is 0, 0, 0, 1, 1, 0, 1, 1. So as it is a multiplexer, for S1 and S0, if they are 0, 0, output is equal to I0. For 0, 0 select signals, output is nothing but I0. So I0 is equal to 1. That's why output is equal to 1 for S1 and S0, 0, 0. Second combination, S1 is 0, S0 is 1. For S1 0, S0 1, the output is I1 as per the 4:1 multiplexer. That's why output is 0 because in1 is 0. Similarly, for S1 1, S0 0, output is 1 because in2 is 1, and for last combination 1, 1, output is I3. So I3 value is 0, so output value is 0. I hope you have understood the gate level modeling. We will see few more programming using gate level modeling. Thank you for watching the video.